Bonjour, mes amis. It's Roger today. Extremely excited. I did something on a Crookes radiometer. I think I fully understand how it works now. So I put out a video on it just yesterday. And I got this from a friend, Erico. He's up in Canada. And he says, this is a double Crookes radiometer. Never saw it before. He said, I've been trying to figure out how it works. And he sent me the pictures of it. And I think I understand how it does work. One of them spins this way, the other one spins the other way. Same light. And he's trying to figure it out. I looked at it, I think I got it figured out. Now, the other thing is, I ran into another guy who is making a proposal. I haven't watched it yet, because nobody understands the Crookes radiometer. Einstein tried to figure it out. He couldn't figure it out. Nobody could figure it out. Einstein was no big hero, trust me. He really destroyed science, so let's just get off Einstein. Later it speeds up, it slows down. It's everything that he said was wrong. But that's just another story. Now, why does this Crookes go this way and the other one go that way? The same light. I can tell you why. I'll show you why. This is going to be a blast. All right, now let's just get started. Okay, my friends, this is like ice cream to me. These kind of things, I love trying to figure these things out. It just excites me. I can't help it. It just does. Now, this guy, Erico, a nice guy, he sends me this thing. He says, hello, Roger. I've been trying to figure out how this double Crookes works. I never saw it before. It says, due to temperature, and this is in quotations, they say, due to temperature changes, such as the sun, the two blades rotate in opposite directions. Same sun. No, there is one source of light, the sun, and yet the two sets of vanes rotate in opposite directions with the same one source of light. How does this work? All right, Erico, up in Canada. Bonjour, mes amis. We're going to figure this one out. Let's take a look. Okay, before we get started, in the other video I did, I laid it out pretty clearly. This has been going on for over 150 years. Nobody can figure this out. And this is a Crookes radiometer I just talked about. And these are the newest theories in 2024. Crookes radiometer explained, finally. And here they go. Wrong theory 1, wrong theory 2, wrong theory 3, wrong theory, current theory. It goes on and on. Now, why is this new theory correct? Well, let's see if it is or it isn't. I haven't watched this. I only got into about a minute or so, and I saw this is going to be fun. This guy sounds like he knows what he's doing, but we'll find out. And here's what he has. The first words out of his mouth is that nobody understands it, and Einstein tried twice and failed to figure it out. But again, Einstein is not on my list of favorites. And he says this is going to get geeky, but not too bad. And I agree. I can show this very clearly. And if anybody can discuss it with me rationally, I would love that. So that's why I have to do these videos against people that aren't physically here, because they won't discuss it with me. So here we go. Okay, he's got this all broken down very well, and this is the newest 2024 theory on Crookes radiometer, and the person that has this new theory is Jerry Z, PhD, Stanford University, California. Now, Dr. Liu introduces transimpact as the driver of the Crookes radar. Transimpact, whatever that means. We're going to look and see what he has to say. And again, I haven't watched it yet, so I'm going to play it and cut in here and there and speak about it. I won't play the whole thing, it's 18 minutes, but I will cut in to the points that are the important points. All right, so let's just start right from the beginning. Okay, the channel is T.S. Brownie, and here he's going to be talking. Here he goes.
This is a Crookes radiometer, and a long time ago a commenter left me a comment and asked me if I could explain this, and it's been a long time, it's been years I think, but I finally got around to it. I used to have one of these, and I think we've all seen one. When you shine light on it, it turns. And yeah, they're a fascinating little device. The interesting thing is how complex they are to explain. It's not just the light, it's what's going on inside here that makes it really interesting. So a little bit of background. It was based on some observations by chemist William Crookes that he made in 1873. He was weighing samples in a vacuum, and he found out that sunlight shining on his samples changed the results. As I said, this is complex and it's still being debated. There's no answer, so at the end of this I'm not going to have a definite answer for you. I've got a pretty good new theory on why it works, and we'll go over that. But I mean, even Einstein tried twice and failed, so that's how hard this is. We're going to get a little bit geeky, especially with the last explanation, but I promise you it's not going to be too bad. A little bit of multiplication and that's it. Okay, on to the next. Some important facts that we have to keep in mind, and one of them is that there is an optimal vacuum level, and that's about 1 Pascal or about this many psi. Yeah, if the pressure is too great, in other words there's too much air in here, it stops turning. If it does not spin, if the vacuum is too hard. So I used to have one of these. I bought it many years ago, and during...
All right, just to be sure you understand what he's saying. A vacuum means they suck all of the particles out of all the gases. All right, so normally it's just filled with gas like the air. Well, you pull them all out, and there's a void in there. Now, you can pull so many out that it won't spin, because it needs some, but it doesn't need many. And if it has too many, it's too much of a resistance to spin. If it has none, it won't spin. And I understand that, and that's because it does need a very small number of particles. And that is part of the reason that it does what it does, is because the number of particles. They think it's just because it's just too much to push through. It's more than that. It's got to do with the number of actual particles in here and how they react to the light, whether they get attracted to the light or they get pushed away from the light. So let's keep going here.
During one of my moves, it got cracked, air leaked into it, stopped working. That's kind of frustrating because I couldn't even find the leak, but it's so tiny. Okay, another thing we have to keep in mind is that the vanes move immediately. There's no delay. As soon as light hits this, it starts turning. And there have been studies that both the black and white sides, sooner or later they reach the same temperature. So as light shines on here, the black side heats up. There's no insulation between these. It's a very, very thin piece of metal. One side has, I think, carbon black on it or lamp black on it, and the other side is just the metal. So very soon the two sides reach the same temperature. And these are all the things we have to look at when we're judging a theory. So the first wrong theory is what I was taught in high school. And
let me just make a statement. What is temperature? What's temperature made out of? All right, what's the difference in the temperature of one thing? Let's say this thing right here, this rock, which is actually a bone, is 100 degrees. Why is this 100 degrees and everything else here is 80 degrees? Why does this come out to be 100 degrees? And why will it eventually turn into the same 80 degrees as everything else is? What they call the ambient temperature, the same temperature as everything else. Sooner or later, this will bleed off. Well, what's it bleeding? What is it absorbing when it gets hot? And if you probably don't know this, and most people don't, but when things heat up, they get heavier. They don't get lighter. The only thing that gets lighter is gases when they expand because they heat up and then they rise. Anything that's solid and heats up gets heavier. So these are some of the facts that most people probably don't understand. Okay, so here we go. These are the current theories, which are wrong. Here it goes.
It's from Osborne Reynolds. It's a very old theory, and he's been gone for a long time. Yeah, he theorized that thermal transpiration was the cause of the movement, and the definition of that is where molecules move from the cold end towards the hot end of a channel only because of a temperature gradient. So the temperature gradient, not because of pressure difference, it's just if you take a tube and you put cold air on one side and hot air on the other, the cold air will naturally migrate to the hot, not because of pressure difference, not...
Exactly. Cold air goes to where the hot is, and hot air goes to where the cold is. And what is going where? What is moving? What is the actual thing that moves? And why does one move in one direction and one move in the other direction? That's the key to this whole thing. It is all related to temperature. Here goes.
anything else but just because of temperature difference. Our channel is the space beyond the edge of the vein. So if we take this section right here and we magnify it, now it's the whole area all the way around here, but we're going to look at one little piece of it. So we have colder air and it just wants to move towards the hotter area, just like we discussed. And it's that mass leaking from one side to the other that causes this to move, according to this theory.
What
However,
mass? Here's the thing. Hold on, my friend.
Earlier, the veins
hold on. What mass is moving? That's the key. Let's get back here and make sure we understand what he's saying. The white, he's saying, is colder, which that is not true. And the black, he's saying, is hotter, which is not true. The white will always be warmer because the more glow there is, the more energy there is. So this is going to really normally be warmer. This is normally going to be colder, the black, until you shine light on it. Then you shine light on it, this gets hotter. Yes, absolutely. This really doesn't change much. Just like outside, you shine light on a white thing and a chair, you can sit on it, it's not hot. You got a black chair and it's in the sunlight and you sit on it, it's hot. That's the key. If there's no light shining, it's just the opposite of what it did. Well, you have to have light shining to give it some kind of a temperature gradient difference. All right, let's just think about this for a minute. All right, this is really where, this is what science is. You're talking through the little glitches. Now, if this was no light on here whatsoever, everything would be this exactly same temperature. They would migrate together and be just basically one temperature. Now, once you shine light on it, it divides the temperature. How does it divide it? What is it dividing? What creates temperature increase and creates temperature decrease? Because that's what happens. You shine light on this. I don't care if you put the white here and the black next to it, and you shine it. This white is going to be less hot than the black. That's just the way it works. Now, this just happens to be on one side and the other. That's why it ends up spinning. I hope that makes sense to you. If you take a black and a white stripe, right, just like this right here, if I shine light on that, and that was on a black board, on a flat board, this would get hotter, yes. This would not change probably hardly at all. It would change a little bit. They get a little warmer, but not a whole lot. This would absorb a lot of the whatever it is that the light is sending. What is the light sending? That's the key. You have to understand what light is, and they don't understand what light is made out of. So they're never ever going to understand these principles or these reactions until you understand the two particles that make up light. All right, so that was the wrong current theory. Now he's going to go to the current theories. And this is from this guy, Jerry Z. Liu of Stanford University. Transimpact model. Now, let's see what this relates to, because I haven't seen this, I don't understand it yet, but I can tell you one thing right now. If they don't understand dipole electron flood theory, this is not going to be correct. That's my original statement. I could be wrong, but we'll find out. Okay, I am just going to let him speak to what this current theory is, and he likes this theory. And because I'm just going to let him speak about it, and then I'll show you mine. I don't want to comment on this because I really don't fully understand it, to be perfectly honest. But it won't make sense unless they understand dipole electron flood theory, and this is just not understood. So here we go.
And he introduces the concept of transimpact. Now, transimpact is the explosive force of a gas molecule's electron cloud expanding rapidly, so its orbital jump, because it absorbs a photon. So he describes it like a kernel of popcorn popping. Yeah, you have the same kernel of popcorn, but suddenly it gets much bigger. And that's what happens over here. This photon comes in here, this electron absorbs it, it immediately jumps out to a new level. And in the case of nitrogen, that can expand the atom by a factor of 7, so it's huge. It pushes against the vein, and it pushes against other molecules in the process. The transimpact energy, so the amount of bang that comes out of this, is proportional to the amount of energy that it absorbs. More energy equals more pop. Also, as an interesting side note, that transimpact also drives Brownian motion. So when you see dust moving around in bright sunlight, some of that is also caused by transimpact. And from the standpoint of the vane, the black side is more efficient. So we'll call it, you will abbreviate that as E. It's a more efficient absorber and radiator of light. So we'll say EB for efficiency of black, than the white side efficiency. So we'll call that EW for efficiency of the white side. So mathematically speaking, the efficiency of the black side is greater than the efficiency of the white side at absorbing and releasing light.
All right, I'm just going to tell you, this is going to get geeky from their side, but what I want to hear from them, or him, or actually Jerry Lou, is what about the cold? We're introducing light, and that does put energy into the system, yes. I don't believe it's doing what they're talking about, driving. It's push to shove. It's field against field, which causes this impact field expansion. But that's another story. I want to know, what if we're sucking heat out? Because this is all heat related. Even though we're working with light, I can do this with and I've shown it. You take a lighter and put it right next to their heat source, and it will drive it the same way as light does. You put cold on there, and it will go reverse. Why? That's the key that I want to know. Does he address that? And again, I haven't watched this, so we're going to watch it together. I'm dragging you through the soup with me from now on. You want to watch? Watch. You don't want to watch? Vayos con Dios. Okay, so here he goes again. This is going to get, this is way too complicated for what the actual reason is, but let's see what they have to say.
We're going to have a number R, and that's the amount of pop we get from the absorption of the photon. And P is just is a constant, it's a number. So if you're using metric system, number will look like this. If you're using standard, it'll look different. And finally, the temperature is in Kelvin. Gas molecules in contact with the vane. So we'll look over here, and we've got this vane, and it's all covered with gas molecules. So I'm not showing all the gas molecules in here. They're awfully thin. As we said, this is a near vacuum. So there's molecules of nitrogen that are stuck to the vane here. And when a photon comes in here, and a photon is absorbed by the nitrogen,
here's the problem. When he's talking about it being absorbed, it's not. It's bouncing. All right, the white part is bouncing off of every other white part. Now, it will be absorbed, yes, into the black until it builds a point where, this is a little tricky, because the problem is they don't understand. Like he said, all these gases, there's almost no particles in here at all. Where the particles are, there's a zillion of them on the surfaces. So they're the only ones really that are going to interact with the light coming in. The ones in here normally that would interact, there's just not enough of them to make much of a reaction. It does get geeky, but my explanation is not geeky. It's just very, very simple, and I've shown it very clearly. So he's going to get into all kinds of calculations about push power and absorption and pops and numbers and and efficiencies. And let me get to a point where I can interject something that will hopefully make sense. All right, his main point here is that the black side will give you what he's calling pops, which are an absorption and re-emission, basically, of the energy that's being absorbed from the light. These just bounce off, they don't get absorbed. So he's calling that a pop. The electron is absorbed into the nitrogen somehow and then pops back out, giving you, I would imagine, a push in that direction. Okay, he's talking about temperature variations between the black and the white side, but he hasn't addressed the reverse of where you're putting cold instead of heat into here. It's all heat related, and he agrees with that, I believe, that it's just a heat related thing, but he's calling it the heat is being absorbed and popped back out of here. Well, what happens when we put cold in here and then the thing goes backwards? it's like, are these unpopping? I mean, when you put light in, it pops, so they push this way, it makes the vein go this way. I can go with that. But when you suck heat out of there, why does it go backwards? That's not unpop. That would be like an unpop. That would mean, I don't know what it would mean. It would mean like this side popping. Right? The white side popping. Why would the white side pop when you put cold in there? All right, it's something to consider. It's possible. The cold makes the white side pop. The black makes, light and heat makes the black side pop. Why? Explain that to me. Why? All right, so this is the current theory, and he's happy with that. And it's I'm looking at it. Let's think about it. Okay, now he's going to do some experiments. This is the fun part. Here we go.
Try something like an ordinary flashlight. And it's a little LED single cell flashlight, and I gotta not bump the table. And yeah, not doing much.
There's something wrong with that flashlight.
Let's try laser pointer. Laser pointers are good.
Red is not going to move it. Absolutely not. Red has very, very little power. What he's showing is red is like this.
Edge. Oh, there we go. There we go. We get a little action out of the laser pointer. There we go. Yep, shoot it out near the corner where it's got leverage.
Interesting.
Okay, there's that. Let's retry the flashlight. See if I can do a...
Why would the red move it and the light didn't? That's just something's not right here.
Closer. It's thinking about it.
He's got that light has no power whatsoever.
Not thinking very hard though.
Let me just think about this for a second. I have red laser here, and I have Crookes, and I have a white light. Let's see if I get the same result. Now he was showing red on here, moved it. Now I had no movement of red whatsoever. Now my vacuum may be different than his. If my vacuum is a little less efficient than his, I may not be able to move it with the red. But for some reason, the white is not moving his. This is totally backwards of what I had expected. And again, I haven't watched this, so you're watching it with me. Like I said, we're going to run through these things together from now on. All right, I'm going to turn the lights off in a second, just so there's no external, influence on this. Now, everybody else is doing theirs in the light. Well, maybe that's good, maybe it isn't. I got a blue laser, I got a green laser, and I got a red construction laser. Now, the red I have found has virtually no energy. Now, this is a pulsed red laser for construction to measure distances. It could be a little different than these lasers, I don't know. But I know that the blue can move it. The green, I don't think I saw it move, but we're going to find again. Maybe red on the very outside edge could have enough to move it. We'll see. And the red I found had no movement whatsoever. Now that was several months ago, so maybe I was wrong. Maybe I just missed something. Now let's turn the lights off, and I will start to shine this in a variety of ways, and I'm going to go get a bright white light. The white light should have moved it. I don't know why his white light didn't move it and the red did. That's just blowing my mind at the moment. Okay, here's the setup. Now, I'm going to just cover up the screen. I use this to cover it up so we don't have any light source coming from behind. And I'm going to turn this light source off here. And now we're pretty much in the dark. All right, now, this is just a white light. I can vary the spot, so I'm going to put it into this spot zone right about here. Now, I'm going to shine it on the black side. Boom, watch what happens. Takes right off. You see it? Boom. Taking right off. See it go? Now, we're going to hold off for a second, let it stop, and then I'm going to shine it on the white side and see what happens. Wow, did that take a long time to slow down? I thought it would slow down much sooner. Anyway, it has stopped. Now, this time I'm going to shine directly onto the white side and watch what happens. It will do the same thing. It will come in the same direction. All right, so now I'm directly on the white side. Look, it's coming towards me. Why would that happen? I'm only on the white. I'm not hitting the black. And the closer I get, the faster it pulls towards me. Why is this pulling towards me? Why? I'm not hitting the black. I'm just hitting the white. Explain that one to me. All right, now this is the red laser. All right, now I'm going to put this shining onto the black side here. Hold on. Well, see, I just turned it. Hold on. This is what it is. This takes time. Okay, this is Rogers' atomic dipole electron flood theory. And Mudfossil University, home of the shocker du jour, is where you're going to find all the details. Now, we're going to go through a lot of little experiments using these different light sources and different heat and cold, and see what effects that has on magnetism. I have found that magnetism appears to have no effect. The magnets I have anyway, and you know, they're fairly strong magnets. This is a pretty strong magnet, and when I come up here and jiggle around, I mean, all you got to do is touch this and it starts jiggling. But the magnet seems to have no effect one way or the other. Well, actually, it might have a little bit of a pull. Yes, absolutely it does. Look at that. I missed this before. It's pulling the white. It's pulling the white. Now let's change the polarity. Hold on, I'm going to let this slow down. You know, every day is a shocker. I had dismissed the magnetic effect on Crookes as there was none. Today I just tried again. I said, well, I got this, you know, it's a pretty strong little magnet. Let me put it up here and see what happens. Now, all you do is touch this and it just starts moving. So you got to be extremely careful. Now, let me come up to this very, very, very carefully and hold it here. Let's see what happens. Nothing. Maybe I was right. Let's try this side. I thought I just had it moving a minute ago. All right. Oh, you know what? Hold on. Let me try this again. All right, this is a little tricky. I have to hold this like a vice grip, because if any movement whatsoever to this and the thing starts moving, because it's just barely secured by a pin. Now watch. I want to see if this magnetism has any effect. First of all, I'm going to go to this side. And it doesn't appear to have any effect. Now, what about this side here? Just letting it sit here. Will it do anything? Will they move? And they do not appear to be more. Now what about this side? It seems to have no effect. Originally I dismissed this as having no effect, but then today I did something and it looked like it affected it, but I see no effect now. That's only moving because I just jiggled it a little bit. All you got to do is, all you can do is touch it and the thing goes crazy. So I think I'm right. The magnetic field does not affect this. And that tells me two things. First of all, there's probably no iron stuff in here because otherwise the magnetic field absolutely would affect it. Secondly, the magnetic lines pushing in to whatever this material is here didn't seem to affect it. So I'd like to know what those veins are made of and what the coatings are made of, because they talk about a couple different types of coatings, some smoke pitch or something, things like that. And who knows? This is just a cheap thing, so I'm sure it's as simple as it can get. But it absolutely does what it's intended to do. The black ends up spinning this way, and even when you shine light on the white, it still it sucks to the light. Very hard to explain, except I think I understand, and I believe it has to do with the glass, as I showed in my last video. All right, so let's do the experiments. We know the white light just makes it spin like crazy, and it sucks the white towards it. Now, let's start with the red. So here we have the red laser. Now, I'm going to shine this right at the very edge of the corner of the black. And hitting the black fully on. Totally onto the black. No movement whatsoever. I put it onto the white. Right out any of the edges. No movement whatsoever. The red has almost no energy whatsoever. Now, let's go to the green. All right, so here we have the green. Now, the green, I can see the green is just barely edging it forward. You see it? I mean, this is just as barely edging forward as you can get. So the green really has no energy either to speak of. Now the blue is powerful compared to the green, and the red is just nothing. So here's the blue. You see the blue makes it take off? All I gotta do is hit the black. Now if I hit the white, it pulls it towards the blue. It's doing the same thing that the white does. Let me stop it, and just to prove to you, once it's stopped and not jiggling at all, that the blue will pull it towards us. This is crazy. This is going on for a very long time. There is no reason for that to be doing that, other than the fact that I just hit it with that blue laser. Now why it's bouncing up and down like that could only be some kind of reaction to the magnetic field of the Earth. It's all I can think. and that this particular pane on this side has all the energy, or lost all the energy or something, which is makes it sort of bounce against the other side. I don't know. I have no idea. This is the first time I've ever seen this. Well, look, it just continues to do this. I'm doing absolutely nothing to cause that. Nothing whatsoever. This is... I don't know even if you can see this. I can. All right, it's just about stopped now. Now, again, I'm going to drag you through the soup here. You want to learn? We're going to learn together. Now, I'm not touching anything at all to move anything. I'm going to shine this light on that. All right, let's just shine it. We're not getting it to move. It's not coming towards the light, which... on a white light it does. It comes towards the light. This just doesn't seem to have enough energy to pull the white towards it. But now I'm gonna back off of this and see if it starts shaking again. Because if it starts shaking again, that's some kind of reaction. Now will it shake? I don't know. It started before. It started shaking, almost like I thought maybe there was an earthquake going on or something. No, I'm not seeing anything at all now. No, it's not moving whatsoever. Maybe it was on just a very uneven balancing point or something that was so unstable that it just couldn't settle. Because I'm not seeing anything whatsoever. So let's forget the vibration thing. But I can make this thing move by hitting the black. You see it? Now, is that what caused? Whoops! Now see, now I just hit it, and then now it's going to shake. All you got to do is touch it, and it shakes. It's probably just an effect of touching it. But we do know that the blue will drive the black, but it will not pull the white. Now we do know that the white will drive the black as well, but it will also pull the white. And here it is, right here. You see it pulling it? It pulls the white. Now you can see it's not pulling as fast as it pushes. You see how fast it pushes? When we do the push part, it's fast. When we do the pull part, it's good, but it's not as fast. So that accounts for why the blue could make the black go, but not pull the white. They're not quite even when you hit them with the same light. They don't have an even reaction. All right, this is the double Crookes that Erico sent me and wanted to see if I could explain it. And I think I can. And the reason is that one set of veins is completely black both sides. One is black and white like the normal. Now, we need to explain why that would cause it to go reverse and why this one would go in the normal direction. And I think I can explain it. And then there's a couple other things I need to explain. There's a little hole with the tube and so forth, and there's a little, I think it's an electrode at the top, and I need to explain the whole thing. Let's just go with that. All right, it's hard to tell much difference between the color variations, but that's the black side, and this is the white side, and the black side would be on the other side, just like mine here. You got the black side is on this side, which is this side, and the white side is on this side. All right, it doesn't look white, but this thing's 100 years old or something, so you're really not going to see it perfectly. But hold on, let me go back to Erico's stuff. You know, this is something to understand here, is I can see there's a black and a white here. The black is here and the white here. Up here, I'm not sure. But this is not supposed to be in this order. Normally you would have the white coming towards us and the black going away, as is mine. You see the white is coming towards us, the black is going away. You see? See the white coming at us and the black is going away? This is the black is coming at us and the white is going away. It should turn in the opposite direction than this one does, because the veins are opposite. It's strictly an interaction of magnetic fields of the particles coming in and bumping, basically, or pulling. And I'll explain that in a minute. Now, the one up above, I'm not sure whether this is dark on all sides or it's the normal configuration dark on this side, which I can obviously see it is, and white on this side. This is a bazillion years old, I don't know. Either way, one's going to go one way and one's going to go the other way. This is just backwards. And that's, now, if it was all black, what would happen? Because I think they might have one there that's all black. This one here. Now, it's hard for me to tell, but it looks to me like they're all black on this particular one. Now, we saw the other one down below was black and white. This is the one at the top, which I think is black all the way around. Now, there's this little thing at the top, and I believe this is where they sealed the glass off, and there was a little electrode put in there to burn something off in there to get rid of the oxygen, basically, inside here, so that they could get a partial vacuum, something along that line. Okay, another thing that I don't think anybody's taken into consideration is that light is always really from one radiant source. The sunlight is coming in one direction, basically. When I focus my lights, they're always in one direction. So it's always directional. That's important. That's very important, because what if I hit this and hit this at the same time with the same lights from one side to the other? What would happen? I don't think anything. Now, what if I had all black and coming in with the white light from here? Would it go this way? Or would it go this way? I'm pushing both of them, or both of them are black. Or would it not do nothing at all? Now, why would it push it? Or is it magnetic? I think it's the magnetism, and it is going to be attracted to wherever that light source is going to be. So if the light source is here, the paddles will pull against it. But no matter where it is, I guess it's going to always go in this direction. Although I don't see why it wouldn't go in the other direction too. I don't know. I'd like to see somebody try it with all black instead of black and white, black and white. But I'm pretty sure. I don't know if the bottom one is affecting the top one with a wind current. Now it's sort of a little bit confusing, because the light source on the bottom, what I understand, is going to move it in the reverse direction, because the panels are reversed, the black and the white. Let's get past that. That one's going to reverse. Now, why would this one go the right direction if it was all black? Would it go in the right direction if it was all black? Is it all black? All right, let's go back to this again. I mean, this is crazy, but these are reversed. Done deal. It's going to go in the wrong direction. Now, this looks like they're all black, but I don't know. I can see that's black, and that's black, which it should be. Just like mine is black and black. Is that white? It looks like it might be white. It doesn't look the same color as the other one. Is that just some kind of a reflection or something? Or because the one in front, this one right here, should be white too. And that doesn't look white to me. The one behind it looks like it could be, but I don't know. This one I would say is definitely black. That one's definitely black. That's what they should be. Now, are they black on the other side as well? And then if they are, what would happen? If the light was coming in from this direction. Now, we know if the light's coming in from this direction, it's going to pull the white. And it's going to push the black. So this is going to spin the wrong direction. Normally, ours spins this direction. This one's going to spin that direction because it's the planes are just reversed. Simple as that. Now, this one here, that's the one I don't understand because I don't understand exactly if they're black and white or if they're all black. And if they're all black, though, let's consider what would happen if they were all black. Let's just play a game. All right, so let's just play a game. I claim that the glass is the reason that for this interaction it has a lot to do with it. Because coming in, you've got light, which is black and white particles. I believe the white particles can come through easier than the black particles, so you get a concentration of black here, which is attractive to white. All right? That's why the white literally is attracted to the white. All right? So, and the black is pushed by the white. So that's why it spins in this direction, and the white pulls into this white, and this white also pushes the black. So white gets pulled into white, and black gets pushed away from white. So that's the two interactions. And this is going to be loaded with black because it holds black particles in here and lets more white through than the black. The black is sort of obstructed and is dense, and the white just sort of filters right through there. And that's why you can see through glass, it's crystal clear almost. Now, the key is, though, if you're behind glass, you won't get a sunburn. All right? If you're out here in the sun, you get a sunburn. You're on the other side of the glass, you see just as good as you can out here, in most cases, basically, but you don't get sunburn. Why? Why don't you get a sunburn? You can see fine, and you can see fine out here, but out here you get burnt, out here you don't get burnt. The only thing difference is this glass. Now, what is the glass doing? It's absorbing these black pusher particles. It's taking them in the matrix of silicon. That's a little hard to understand, but trust me, they are absorbing these heavy particles and allowing the white ones to flow through, more or less unobstructed, but not powerful. So it's eating up some of the white ones too. That's why you don't get the sunburn. Because if all the white ones came through, you'd still get the sunburn like you did over here. It's the white ones that give you the sunburn. But the black ones are the ones that really force them into you. So if they're stopping here and you're just sort of getting fluffed up with the white ones, but not the full extent of them. Out here you're getting slammed in because the black ones are pushing them like crazy, and you got full account of them. Here they absorb, some of the white ones are absorbed and more of the black ones. So here you get still more of the, you can see it very easy. It's a glass, so you can see it fine, but the stuff that would damage you has been absorbed basically by the glass. So now, so we have a preponderance of dark here. That's my claim. And we have a preponderance of white here. So this is basically a dipole at that layer of the glass. Now, what would that dipole do to these? Because these are dipoles too. One side's black, one side's white. That's a dipole. Because one side is going to have less electrons than the other side. That's the more radiation you get from something means the more electrons it has as radiating back at you. All right, the less radiation you get back from something, it goes towards the dark black. And once you get to where there's almost no extra electrons, you're into pitch black. And it gets colder and colder and colder as you get darker and darker and darker, basically. All right, and the, you know, in the darkness of space, let's say, that would happen. But when you send light into it, it gets hotter and hotter and hotter because it wants those electrons. So normally its ambient temperature is way down there where there's very few electrons in it, but it's still the same sort of temperature as everything around it because it's built to a specification that says, I don't want electrons in here, I'm a black layer. Well, when you force those electrons in with light, it heats it up. If they're forced in, they're going to heat up, and that's when you get temperature change. And it's because it's absorbing these extra dipoles, and not just the white, it's absorbing both. And when you give off heat or take in cold, you're giving off or taking in both particles, the black and the white. All right, that's what temperature is, the black and the white particle together coming in to whatever the material is. So they float around. That's why you can get ambient temperature. You come in with something that is like this. I think I showed this before. Let's say it's 100 degrees. Everything in here is 80 degrees. After a while, this will be 80 degrees, and everything else will stay 80 degrees. This might add a little temperature and it go to 81 degrees. Whatever. There'll be just electrons flowing out or flowing in, and it depends on where it came from, a cold area or a hot area, and there's other factors that forces the change temperatures. But the point being is, this is either absorbing or giving off complete electrons, which is the dipole, black and white, is the flow in or out of this. All right, and that's basically what an electron is a dipole. That's why I call it Dipole Electron Flood Theory. So we have to deal with the full particles, but here we have a dipole on its own. So we almost have like a magnetic field surrounding this. You might want to think of it that way, where one side has a lot of extra electrons and one side has less electrons and has more of the positive, because you can separate these black and whites when you get down in the subatomic realm in light. Very simple to do. I never realized. I just thought it was impossible, but they separate very easily. So this is going to be dense with positive, this is going to be dense with the negative, and that is almost like a bar magnet. And the stronger the light coming through, the more the differentiation will be. This will get more dense with dark particles, and that'll be more dense with light particles. So the dipole gets stronger and stronger and stronger. That's why white is real strong, and you get a big effect. And red, it just really doesn't bang hardly into anything. Red is just, you're really not changing the effect much at all with the red, so you don't push. Okay, just so you understand, this channel is T.S. Brownie, and this is Crookes Radiometer Explained. This is the newest theories. He's a good explainer. Now, I have a different take on it, but this is what research is about. You look at one guy and you say, well, what about this? Can you explain that? Because some of the stuff he showed, very interesting, hard to explain, but I think my dipole electron flood theory basically covers that. And again, this is it right here, dipole electron flood theory. The anatomy of a proton is all dipoles. It's not just one big solid positive with one tiny little negative. It's all dipoles. And everything there is made of these two particles. That's the only two particles that exist. And I have shown these particles over and over and over, many, many, many times. And they are the same ones they found at Fermilab. There's no difference. And we found them here using light. And we actually split them, which, for all practical effects is fission, and they came back together, that's fusion. They were the muon and electron neutrinos when they were attached together up here, which is a strong nuclear force. When they divided down below after hitting the Venturi here, They exploded and separated, which is fission. The black broke away from the white. The white went separate. They call that a sterile muon. See this muon up here, muon neutrino? That's what that is. It's separated now from the white particle, which is the electron neutrino, now becomes the electron shower. Then they come back together. And the reason they did that was because there's a venturi here, which is a very tuned orifice that forces all the fields to crush together. The same thing they do in the particle colliders, only we went sideways. They went head on. And they're just going to go like this and like this and like that. We get them here, there's nowhere to go. They have to crush. And so it's a very efficient system, let's put it that way. And it's the same particles, identical. And he says this black one can have a glowy edge, which it does, and they have a glowy edge, yes. And the white one is a puffy particle, has no real mass. And I agree with that 100% as well. So all the things that they're saying, I agree with. And this is in outer space where dark matter has been collected into the center, and the white charged particles are pushing it in. And the only reason we see in the white particles is because they're shining light into it to observe this. So they're reacting. And then they saw this on Earth, and the guys freaked out. One guy locked himself in his office for 3 weeks. Now, here's the problem they can't explain. Something just came in. I'm going to show you in a second. But look at this. The sun's corona is millions of degrees out here. On the sun, it's 10,000. On the Earth here, it's 100. Out here, it's almost 3,000 degrees. Nobody can account for this. I just got a thing in from, well, I'm going to show it to you. They still can't account for it. They're trying to make up all these things. Now, I've been talking about the reason is we're scrubbing through all the particles in space. Everything's spinning and they're ripped through it, and that's why all of our ionosphere and the sun's corona are scrubbing through space. That's what is grinding through there, and that's why we have an ionosphere and they have a corona. It's just saturated with electrons pushing and shoving at that one point. It's called the Kashmir effect. And at that one point, you're going to have electron-to-electron interaction. All the dark particles are going to split back. And that's why you have the ionosphere is just almost 100% ions. Okay, there's certain things that are undeniable that people are just denying now. I call them deniers of reality. It's very simple to see with the telescopes and everything. They've been seeing, this is reality, that we are spinning through space on an arm of a Milky Way, and we're ripping through space, and we're spinning on our axis, the Earth, and also ripping through the Milky Way along with the sun and spinning at the same time, orbiting the sun. So we have a lot of activity going on. Now, here's what's going on. The scrub of the sun spinning and moving forward at the same time, and I can prove this, what I'm saying, is forcing these particles as a field to go through and scrub all these particles that also, they have to get out of the way, and they don't want to get out of the way. They're just laying out there having a good time. But this thing comes through, and that creates millions of degrees scrub. It's like a fireball coming through the sky, and it is. As far as I'm concerned, the particles in space make space a sky. It's not just nothing. And they say it's nothing. It's not empty, it's full. All right, there's no question about it. And all light that goes out is going out as particles. They're so tiny that they don't really obstruct anything to speak of, but they have a very significant impact on everything, as I will show you. So we have an extreme scrub here. They have an extreme scrub here, where our electrons meet the space electrons. The same thing with their electrons meet the space electrons. Millions, 10,000, 3,000, 100. Nobody can account for it except with electron flood theory. All right, so what I'm showing you here, nobody can deny this. The only people can deny it are these kind of people, deniers of reality, doors. All right, those are the doors. From now on, I'm going to call them doors, D-O-Rs, deniers of reality. You can't deny saying that the space station doesn't exist and all that stuff. You can see the Earth is a round ball, it's spinning around. This is not in question. We are in a cloud of everything. This is a picture from a cell phone with an app that picks up magnetic waves. This is the moon. And this is some kind of thing behind the moon. I believe it's probably, well, it's got to be some kind of planet, I imagine. It's giving off all of these magnetic waves. The moon does not give off the magnetic waves, but all this stuff is in space. Light comes through there and slows down. Deniers of reality in academia say, oh, no, light just keeps going the same speed forever. No, it doesn't. They are deniers of reality. They've come up with these laws like Einstein made. Light goes the same speed, never slows down. Einstein destroyed science, absolutely destroyed physics, and they keep touting him as, oh, even Einstein did it, even Einstein said that, or even Einstein. It's just nonsense. Everything he said was, literally everything he said was wrong. But they didn't know about dipole electron flood theory. They took this Bohr theory and just went with it. It doesn't work. So this is what all light has to plow through. When it plows through this, it slows down. Nobody can tell me that it doesn't slow down, and they know it doesn't slow down. And I can show you it doesn't slow down, even in not a vacuum, which they call this a vacuum. There's no vacuum there. There's just thousands and thousands and billions and trillions of light particles and everything. And even Fermilab says it's saturated with these particles. And they wink on and off like a bubbling soup out there. And it's true. That's just what it is. There's just nothing but particles in space. It's completely saturated. It's like the mist that condenses into water, and it's the mist of light. I call it atomic vapor, and it is atomic vapor. I wrote that in 1970. Light is atomic vapor. As a matter of fact, I will get that paper. All right, here it is right here. The transfer of energy is from light to atomic vapor. That's what everything out there is. There's little tiny atomic bits. They're dipoles. This was my theory way back then. I based everything on Millikan's oil drop experiment, the weight of an electron. That's how I came up with 1823 make a proton. Because if an electron weighs 0.000585, something like that, you take 1823 of them. That's what he says it weighs. You take 1823 of them equals 1 proton. So I say an electron is a dipole, and you take 1823 of them, it makes 1 proton. And the transfer of energy is from light to atomic vapor. Atomic vapor is just like moisture, like atmospheric moisture. You condense it, it turns into water. You condense atomic vapor, light, it turns into matter. Basically the same exact thing. And the reason it turns into matter is when it's being forced down onto the surface of the Earth, because the Earth, it has to be saturated with dark matter, the black parts, because they suck their way into them just absolutely voraciously. And that's what electricity is. When you take lightning, right to ground, that's the white part coming down to the dark part. It was the ground. We call it ground. They want to go to static. Right down. Electricity, you put your finger up there and plug it in, it'll go through you right to ground, explode you like a bomb. It goes through trees. Well, you know what lightning does. I mean, everybody does, and some of them is extremely intense lightning. Some of it's not quite so bad, but it's a discharge of particles of only the white. I believe, that's my belief at this point, is virtually only the white. Well, you know, it's hard to say. It is hard to say, but I think the white is just escaping just because there's just too much of it. Because you know, I never thought of the white and the black being able to be separated. But when I saw this experiment in 2015, the Russians did, I could see, yes, you can divide the black from the white. And as this experiment progressed, this thing just kept going boom, 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 boom. The white particles are forcing the black to congest in the center, and then it just crusted around them. That's my dipole electron flood theory. And then they showed a whole bunch of other things, and actually DNA, spiral-looking things coming out of charged particles in space. I don't know. Where did life come from? Did it just originate because these particles want to find each other in a helix shape? And then they form these little bars between them for some reason? Everything is up in the air now. I mean, everything is so up in the air now, it's unbelievable. But let's get back to the heat issue. Here's the sun. Right now, they have no idea why the sun is so hot. I mean, the corona is so hot. Well, out here, the sun is here. That's the surface. Let's take it right here. That's the corona. We have the Earth here. Right out here is the ionosphere. Now you've got these little springy looking things coming down, showing they can come down in weak looking particles. They can come out very hard, heavy duty particles, which cause problems in the power grids. Now the moon will only re-radiate. The moon does not radiate, I don't think. So I'm going to say it re-radiates. So whatever it glows, it bounces back. So it's going to be in the red spectrum. Now, why is it 3,000 degrees out here? Because we're scrubbing around like this, going through all these particles that are in space. I mean, the particles are everywhere. And they have to be pushed through. And as they do, they scrub and create our ionosphere. Now you got electron to electron. They hate each other, the white particles. So that is where you create that barrier zone. And the same thing here. As they come out, as soon as they hit all the space particles, which they're just saturated, they start to glow like crazy right out here, and you get millions of degrees versus 10,000. You get 3,000 versus 100. Simple as that. And all the temperature charts and all that stuff you can see here on Earth, it shows it. You see? The ionosphere. Ion means electrons. Ions are electrons. 1,500 degrees Celsius. That's 2,700 Fahrenheit, something like that. And then exactly in the dipole layer between, it goes down to minus 80 Celsius. That's 112 below zero. That's your dipole. So what does that mean? The hotter it gets out here, the colder it gets here. All right, the hotter it gets here, the colder it gets here. The colder it gets here, the hotter it gets down here. And that's where we are down here. That's why we are getting global warming. This is getting colder. They know this is getting colder. I saw an article the other day that said, well, it seems like the mesosphere is getting colder, so maybe global warming is reversing. No, it is that gets colder, that's going to get hotter, which is us. And then you get to the Earth, which sucks up all those electrons, and now the water in the Earth is overheating because it's got too many electrons. And it's because we have gassed off so much stuff that these layers, which used to be sort of low and not too bad, but we've filled them up like a balloon now. And so we're scrubbing way harder than we should out here. The turmoil is just incredible around the Earth. And it's getting worse and worse. The more we burn, the worse and worse and worse. And the more we burn, and then fires all over the Earth, the more that burns. The more that burns, the bigger this gets. And it's a runaway train as far as I'm concerned now. I don't see it ever going to be able to be fixed because we're fixated on oil in the first place, where we should be looking for alternative fuel sources. I mean, we destroyed the planet, and now we're destroying the atmosphere, and that the atmosphere controls the crops, it controls the water, it controls everything. So I don't want to be a bearer of bad news, but I have no good news to report at this moment. Okay, so again, these are the particles. This is the problem. I have shown these, and they don't want to see these because I'm not going to say why. I forget that. But this is light. This is light. Those are photons. We can see these using the experiments where we were using. And CERN now is doing something very similar. They're using CMOS to see their results too, but they're using big heavy particles getting a whole lot of debris. We started with the most basic particles that exist is light. We started with light, so we didn't have to dig through all that debris. All right, coming off the sun, all that is debris. That is debris. It's particles. It's light. It's sun. It's all kinds of particles. And when they hit all of the things in space, they just and they scrub through there and create enormous amounts of energy out there. This is a solar eclipse. That's the moon. But we can see all the particles are going out. And Fermilab says, yes, it's just saturated with particles. See, this is quantum foam. And they realize this now. Nothing doesn't exist. There's quantum foam. And this is Don Lincoln talking about the quantum foam. And they're showing images of it. But what it is it's particles in space. And here's the Fermilab thing. And this is when I had some interaction with Don Lincoln, a little bit. And here he says right here, empty space isn't empty. It's saturated with this quantum foam. Now he also had the point particles. Hold on, let me do the point particles. Because that's what we found was the point particles. That's why I contacted him about it. Anyway. All right, this is going to be Don Lincoln again. They're talking about point particles. And this is his article about it. Again, over 10 years ago. Now this is the point part. Here they are right here. These are the ones we found. Exactly the same particles. I can see no difference whatsoever. And he says that the black one and the white one, or the glowy one, and the glowy one has no mass and has all the energy, a field, and this one has no, has all the mass and a glowy edge around it. And that's the particles we found. As a matter of fact, I just showed you this right here. There's the particles I just showed you from the Fermilab article, and here's the ones we found from light. Now, they come green, they come red, they come blue. And the difference is the red and the green we show coming through the Venturi at the same time. The green is much more powerful than the red, and the blue is much more powerful than the green. That's the spectrum. So I've shown all this stuff. Now, what we want to do is look at this. He relates to the quantum foam here as well, where these particles exist in the quantum foam because they're light. He says, in summary, the extended particles, that's the black one, have a fixed size, never change, ever change, that's the black one, and I agree with that. They have a fuzzy edge, I agree with that. The point-like particles, which are the white glowy ones, in the red, green, blue, whatever, they're a mathematical extraction with zero size. This is where I get a little stuck on the zero size. There's got to be something creating that field. I haven't figured it out, but there's got to be something. Anyway, he says even zero-size particles have an extended effect due to the effect of the field surrounding them. But surrounding what? If there's nothing there, what are you surrounding? If there's a zero size, there's something's got to be going on there. I haven't figured it out, but it's got to be almost like it starts off with the tiniest little thing that almost is nothing, but it's like a soap bubble, and it can blow up into a bubble, and then it creates a field, yes. And they actually have very distinct borders on them, almost like a bubble. So that's possible. They have to have something there. That's what the thing that's killing me. But anyway, there's no question these are the same particles. I mean, as far as I'm concerned, these are the smallest particles they can find. And we also found those same particles, but we started with light, so we could see them very, very clearly. And in green and in blue as well. And those particles fill space, and they scrub, and they bump. And when they do that, they create energy, and they slow down in space. These telescopes saying, oh, there's 50 billion light years away. No, they're not. They're coming down, the light is slowing down. And I think it's slowing down pretty damn fast. Because there's so much debris in space. Look at this. This is just our neighborhood. It's everywhere. It's everywhere. It's just everywhere. Everywhere. There is nowhere you can go where you're not in the midst of debris. It's just like Don Lincoln said, empty space is not empty. I concur. Okay, I'm sure you're probably getting bored by now, but that's a dipole electron flood theory. So I'm going to leave it at that. These are all the things I have just shown you that support the things that I'm saying. And if you want to look up dipole electron flood theory, very simple, 2-3 minutes you can know the whole thing. It's ultra simple. It's on dipoleelectronflood.com. All right, now my good friend Oscar Rosales did this and did a fabulous job. This is what I consider to be the proton. Now I did have this other one. This is this one here where it's separated in the black particles in between the layers of the glowy particles, but I don't think so. I think it's this one here. Let's go with that. And these are the two particles that make up everything. And this, watch, I'm going to scan through the whole thing. These are all the particles from electrons, muons, only two that make up anything. They can form neutrinos of all different power, basically, intensity. Two of these back to back make a gluon, which we always thought was an electron. Two gluons together show, as I showed you, the photon. And then 1,823 of these make up what we would always consider a proton. Some changes in chemistry, some changes in space. Redshift goes, space changes a lot. It changes everything. It changes the periodic table. It changes chemistry. To understand the half-lives and enzymes and biology, you have to use dipole electron flood theory. You cannot create the reactions that enzymes create without being able to break these particles up in these specific ways. Enzymes are the things that create everything in life from bacteria. So this is a very, 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 very broad range of research. It stretches from nothing all the way up to everything. So I'm gonna, like I said, I'm gonna leave it at that for today. And as you know, I just sort of put one foot in front of the other and just keep going. Now, I'd like to see some people get more invested in this and understand this, and more thumbs up, and you know, try to help out a little more to get the thing out there. I've tried to contact a lot of people. I've given up contacting people. I just get no responses. Everybody says, "Oh, contact this guy, contact that guy." They never contact me back, so I gave it up. If somebody wants to understand this stuff, I'm literally the only one that understands most of this. I'm serious. The astronauts, these people in NASA, they don't understand any of this stuff. They don't even understand global warming. They don't understand the corona. They don't understand gravity. They don't understand how heat and light works. I'm serious. I mean, I'm literally serious. Unless they do, and they're just not, being honest. They don't understand Mars is completely saturated life. The Mars Morse code, the Mars crabs, the Mars blueberries, all biological. And I know they must know this now. So, we need to have more exposure and people stepping up and saying, why aren't you people paying attention to this? What is going on here? What is the story? They're working with taxpayer money, my friends. This is not something they're doing for free. And they, I don't want them just walking around in circles spending my money. I don't know about you. Anyway, I'm going to leave it at that. Again, thank you. I love you all. Hopefully we get this understood and we can progress forward. That's all I want to do, is progress forward and get some knowledge and understanding, and open the forum to people that are excluded like me because of peer review and the suppression of my information by academia. So I'm telling you, they can just force you into oblivion and nobody ever even know you ever existed. And that's what happened like Velikovsky. When I started with this, I went out and said Velikovsky was destroyed by these academics and he was right about everything. And I contacted a ton of them. And I had one or two responses. Who's that? Or, oh, that crazy guy talking about dragons and monsters and Venus hitting Earth, they laughed like hell. And that was it. Not a single one of them paid attention to anything. And that's what we're up against right now. So if you don't start speaking up, this is just going to go on forever. You know, I thought it would have to, with all the evidence and the CAT scans and the DNA and the specimens and all of the things that I showed. I figured for sure somebody's going to have to step up and say, yeah, let's take a look at this. Nope, never happened. So, once again, I still love you. Good luck.